Patricia is an expert both in the actual modeling of waveforms, particularly phenomenological waveforms, and also data analysis. She's one of the co-chairs of the parameter estimation groups in the LIGO-Virgo cognitive collaborations, and today she's going to teach us how to do things.
Thank you very much. Thanks to the organizers for having me. So thank you for being here this early morning and ready, hopefully, to get started looking at some actual data now. So Erin gave this wonderful introduction to the tools and the mathematical background of some of the analyses that we do yesterday. So we thought when we discussed the layout of the first week that maybe it'd be a good opportunity for folks who are not in the gravitational wave data analysis side to actually play around with some data, try some of these things, compute a power spectral density, do a little bit of parameter estimation, generate some waveforms, etc. So this is kind of what this tutorial is meant to cover. I didn't do all this work by myself. In fact, most of this is ripped from other people's great tutorials that you can find online. In particular, the first link I'll point out. Every year, the LIGO-Virgo collaboration holds an open data workshop, which is mainly aimed at folks who would like to get started with data analysis of gravitational data, covering way more than I would be able to cover in this 1 hour. There's also accompanied by some lectures that you can stream online and then watch the recordings, etc. So if you want to know more, then I think this is a good starting point, and then you can dig deeper depending on which of the topics you're interested in. I've also listed links to the main documentations for some of the packages that we'll be using, but don't worry, you don't have to install any of that because we're going to use the magic of Google Colab. So no worry which platform you have, which can be a pain to install things on. So we hopefully are going to circumvent this. So to get started, I'll have you all go to this GitHub page if you haven't already done so. And you don't need to clone the repository. That's the magic of Google Colab. So you can just click on that button, which says Open in Colab, and that should open an IPython notebook for you on the cloud, which, let me know, is this working for folks? Work for Aaron?
I found what is it here?
The little badge.
It's a little button.
Here,
Open
the
it
badge
up.
here.
Oh,
So you click on that.
And then the rest.
Oh, hang on, there's a laser here.
Yeah.
This one. So you can just click on it, and it should open this notebook for you, hopefully. Wait 30 seconds and then wait for noddings or like, no, it's not working.
Sorry, I missed the link.
You missed the link. It's the little badge on the GitHub page. So if you go to that GitHub page, and you see that little badge there that says Open in Colab. Yeah, and it is case sensitive, so please do spell these with capital letters here. Okay, while people are getting started on Google Colab, hopefully it's not going to die. I'll briefly say something about the packages that we'll be using. There's many, many more. All of our software, in fact, is public. We're required to make our analysis public, so you can get everything. And here are some that are core and some that are very user-friendly, I would say, to use. The big core package of algorithms that we started out with using, it's now proliferating a little bit, was the LAL suite repository. So I've linked to the docs here, but you can also download the full repository, which is mainly coded in a specific version of C and can be a bit clunky to get into for students, but it has nice Python wrappers. And that's really the big algorithms library that contains many of the functions and utilities that we use in our everyday data analysis, including the vast majority of waveform models that Maria and Garen discussed in the first 2 days. You can access them through this library. They're coded up in there, and that's actually what we mostly do. Now we're moving slightly away from this. There's now also kind of a Pythonic movement, I would say, that's happening here, where newer waveform models like SUV and RP5 that we heard about Garen's talk now, for example, is coded actually in this nice Python framework. You still access it through LAL suite, but with a slightly different functionality. But the core code itself is no longer contained within that library, but it's external. We also generate normally our noise through LAL suite, LAL simulation in particular. We have old inference code in there. So that's really like one of the core things, and you can pip install it if you want to, so you can get easy access to this as well. The other thing we're going to use is going to be GWPy. So GWPy is also a nice kind of Python library that in particular is designed for access to data and manipulating actual data that comes out of problems. So if we're doing FFTs or we want to compute power spectral densities, that's when we use GWPy most of the time. And it's quite accessible. Documentation is okay, can be a bit tricky, but at least there's some. We'll also be using PyCBC today, which is another Python library that was initially specifically designed for searches. And in fact, PyCBC is one of the flagship match filter searches that we use in the full duration. Colin, who isn't here today, but is still going to be around also next week, I believe, is one of the experts and key developers in PyCBC. So if you have any detailed question on match filtering, you should definitely take the opportunity to talk to him. We will in fact be accessing the waveforms that are coded up in last week through the PyCBC interface just for convenience. You don't have to do that, but that's what we're going to be doing today. And then last but not least, there's the link to Bilby. So Bilby is one of the inference libraries that we use more or less now, our core inference library that we use for LIGO parameter estimations. So that was the final point that Aaron mentioned in his talk yesterday, actually characterizing our sources. So this is where the likelihood function is coded up, for example. And that's what we will also be using a small example today, so you get a flavor of how to do gravitational data analysis in practice. Okay, that makes sense to everyone, but now everybody has clicked on the color badge and was able to open a notebook. Perfect, cool. Then we can move straight over. So first things first, you need to connect the kernel on the cloud by clicking on the connect button in the corner. I take a moment. Work to everyone. Okay. And then, so if you, I don't know if you have used Google Colab before, but it's essentially just an ICTP notebook in this particular case that you're set up here. Everybody familiar with ICTP? Has used them before? Yeah. Okay, so IPython is just kind of the kind of, yeah, exactly. It's what you access through the Jupyter server normally. And it's just kind of a nice GUI interface rather than just having a Python script that you're running. Think of it as the kind of low-level mathematics. The nice thing with Google Colab is it loads all the base packages normally in the background already for you, so you don't have to install those. But what we do have to install are these special packages that we want to use, and that's what this first cell is going to do for you. So if you just run it, you can do either the Command Shift or click the little play button on the side, on the cell. And so what we're installing here are these packages that I've mentioned before. So we'll be installing GWPy for the data manipulation aspect, PyCBC then for, in this particular case, generating some waveforms, Lal Suite, which contains the waveform code, Bilby, our inference package. And our inference package also has dependencies on other packages. In particular, the samplers that we will be using today will be Dynasty, which is a sampler developed by Josh Spiegel. So that's an external Python package that will be loading in. You can use different samplers. You can write your own sampler and hook it up. It's completely
By sampler, you mean samples of what Aaron was talking yesterday about.
Yeah, so that's the implementation of how you actually solve this complicated 15-dimensional parameter space problem where you initialize your walkers and walk through. And the different methods you can do that. Aaron described the heuristics for troubles out there yesterday. We'll be using nested sampling. Yep.
Is this being installed in the cloud?
Yeah. Nope, it's all in the cloud. If I'll leave you an allocated cloud space.
Google.
Google, yeah.
They're actually very generous.
Yeah. You can get I mean, it's limited in terms of you use the free version here of how much cloud space you get allocated and how many cores you can use. But if you pay for the plan, which is really cheap actually, like almost infinite cheap. Okay, this should be very quick. So it's all packages installed for me already that work for everyone. No error messages creeping up somewhere. And then we just load some of the base Python packages that everybody is hopefully familiar with, matplotlib to do some fancy plots, and NumPy for standard operation. Morning, Colin. So Colin is your PyCBC expert. Okay, so we don't have to go through all of this. We obviously have an hour, so we can look at the preferences what folks want. And the idea is here, I put some base examples, but it's all for you to explore and to play around and change parameters. And you know, if you want to do waveforms, go to the waveform section. If you want to do PSDs, go to the PSD section. Give you a quick overview of what's contained in here. First example is, how do I even access data? All our data is public, post runs, so we can look at all the previously detected gravitational wave events. We can download the data around those events. As Aaron mentioned, these are stretches of 4,096 seconds. We can play around with them, generate the power spectral density, actually analyze the event itself, etc. We can generate some spectrograms. Everybody know what a spectrogram is? No, that's what I thought. Spectrogram is a time frequency representation of your data, and that's particularly interesting when you want to compute or when you want to get an understanding of how, for example, the detector behavior is evolving over time, which we heard as well today, right? Our detectors, they are reasonably stable, but they're not fully stable, right? So there is evolution in how the noise floor evolves over time, and you can visualize that very nicely using spectrogram. We'll then look at something called Q transform. This is a very special type of a spectrogram where we can pick out very particular features. And Maria was actually the first plot that Maria showed in her talk on Monday, where everybody had seen this nice chirpy picture of GW150914. So we'll see how we get to that picture. How are we actually creating that type of representation? And then actually, how do we generate a power spectral density for a given stretch of data? There's a section then on waveforms, different types of waveforms, different models that you can call, how you call them, and the different physics they include, and how the different physics manifests itself in the waveform that you're actually creating. Because I know everybody here says they calculate waveforms. Many people never ever even look at waveforms. So that might be a good opportunity. And then at the very end, we have a parameter estimation sample, a simplified parameter estimation sample, so that it actually runs in like 10 minutes on your computer for 1509. Okay. All right. Maybe we should look together at access to data, because that's the first starting point. So we have something called the Gravitational Wave Science Center, or GWAS, where you can download essentially all our data. So if you go to gwas.org, you can get all the strain data up to the end of 03. That's publicly released and available for you. And you can get all sorts of other data products as well. But right now, we're just interested in just downloading actually the stretch of data. And in this particular case, I've chosen 150914, the first gravitational wave event. So we're going to use GWPy, and we just import from them the time series object. And there's a function that allows you to query the GPS time of a specific event. And that will determine what stretch of data we're going to download. So in this particular case, this is the GPS line.
GWRSC is in the GWP.
Say again?
GWRSC that you are loading there is also in the GWP.
That is already loaded for you. You don't have to. Yeah, it's just a simple package you can import. That's pre-installed on the file. So it should work for everyone. I hope it works for everyone. And then if you evaluate the GPS function, it just tells you what is the GPS time of 150914, which was sometime like at 9:30 in the morning or something like that. And then we decide on how much data around that GPS time we want to actually download now. So I've chosen here, okay, for L1, so like a Livingston here, I'll choose 8 seconds before this GPS time and 8 seconds after this GPS time. So I've got a stretch of data that is 16 seconds long, centered around my event time, in this particular case, 150914. And GWPy does that all very nicely for you. So it's literally just querying the server and pulling that data frame for you. Work for everyone, hopefully. And you can do the same for Hanford. Why not Virgo? Question for the audience.
Why not?
Virgo, the Italian detector. Why am I only loading Hanford and Livingston?
Was not
Excellent. Everybody's awake. Very good. Okay, so you can see the output here a little bit. So it tells you what's contained in here. We have the time series data, but what time series data is it actually? So it very nicely tells you it's strain data, which is exactly what we want. And that's what we want to analyze. It also tells you the start time of your data stretch that you've just downloaded here, and what the time sampling is. So what's the increment between two neighboring data points in the time series.
So it's just a question, so this, of course, you're targeting a particular event, but as you not knowing that, you can just go back and chunk after chunk after chunk.
Yep, exactly. I mean, in this particular case, because we're using public data, right? We're downloading something that's interesting. You can download any structured data you want. You don't have to start from a 15-minute or from any event that you have. But of course, for this audience, I thought it would be interesting to actually see. Yeah, then you have to talk to Colin about how to set up your own filter structure to find your own.
And there is required for the time figure. Then I would just, if I want to pick an arbitrary time.
You can do that as well. Yep, you can pick an arbitrary time. Now, what could of course happen is our data that's released publicly is not necessarily continuous. There are times, of course, when the detectors were down, so there's no data generated during that time. It could also be time where the detectors were on and data were generated, but they were contaminated by something. And so normally we do not release those data. So it could be if you pick your birthday, for example, that maybe, there's actually data. So we'll tell you, sorry, no data there. Now that we have downloaded the strain data, let's look at them. How do they actually look? So we can just plot, remember, it's a time series. So we can just plot this time series. That will take a little bit because we have 16 seconds of data here, sampled quite finely. So it's quite a long array that you plot in here, but it's nothing more than just an array of the time series. And I know you guys came a little bit later. If you have a laptop, or if you want to pair with somebody who's got a laptop, maybe if you want to click through it. Nope. And I just repeat it in case you want to play around at home alone. You don't need to clone anything. You just go to the GitHub page and you click on that little Google Colab button, and it will open the notebook in the cloud for you. All right, it's finally done something. So the first plot here is the strain data now. So we're plotting this time series. You can see it's 16 seconds long. So that's what we downloaded for the LIGO Livingston detector here. So I stuck to the standard color scheme that LIGO is using: blue for Livingston, red for Hanford, purple for Virgo. We don't have Virgo in this case.
So just a question on the matter of dating. So you fetch a particular time when minus plus 8. How does LIGO label the time by the peak of the waveform, or?
It's the peak. Well, it's the peak time of the SNR time series.
But then I guess when we do parameter estimation, it depends on the waveform.
That's right. That's right.
Yeah. Different waveform models might define relative time slightly differently. Most of them are all kind of conceptually unique, but there's some variation.
And it's also true between the different searches that ring off, right? They will have slightly different template banks, slightly different template that will actually ring, which will define a slightly different peak strain time.
This is for CBC, we work on continuous mix source.
Yeah, I think we'll have a whole different session with these words. Okay, so it's finally plotted our time series, and you can see that they do look quite different between the two detectors, which is what you would expect. The detectors are obviously in different locations, they have different noise sources, they have common noise sources, but then of course it all depends also very much on the environment, as Aaron was talking about yesterday. They also weren't operating quite at the same sensitivity at the time, and they are not today. So if you look at the current status of the detectors, you can see that Livingston is slightly underperforming Hanford at the moment. But I point you also to if you look at the kind of the magnitude on the axis here, you can very nicely see that. All right, so we have data now. We can generate a program. Sorry, I didn't mean to run all of them, which I accidentally did. So you can code this up yourself. So back the spectrogram, essentially what we're doing here is we're taking our time series. Right, so you've got a structured data. which is from T naught to my Tn, right? And what's happening here is I break it up into smaller segments, where each segment has the same length. And then you worry about edge effects when you go into the frequency domain, as Luis was pointing out yesterday. So what we actually do is we produce segments that are overlapping to some degree through the entire time series here. And that's exactly because this is time series data. We saw yesterday that we naturally characterize the performance of the detector in the frequency domain, so we have to do FFTs. With our time series, of course, doesn't go to 0 at the edges, which is what would give you a nice FFT, of course, so because of the periodicity condition. So we have to kind of artificially construct that. And we do that by having overlapping signals where we window the edges of each of those segments. So you do this for each time, for each segment, and then the spectrum averages essentially over the frequency content of the frequency bit. So that's kind of what we see here. This is, by the very definition, normally an energy content, so like an amplitude squared, that will define essentially the color of your tile and your time frequency tiling here. If you don't want that, if you actually want to look at strain, which is the quantity we're most familiar with, you have to take the square root. So that was the difference between the power spectral density eventually and the amplitude spectral density, but also area expansion. So if you run this, you get this beautiful blue blob, which is like, oh, well, what am I going to do with it? Is this telling me that absolutely no variation over those 16 seconds and it's like equally sensitive in all those frequency bins? No, it's a plotting artifact. So what we want to determine in order to make the color scheme appropriate is what is actually the minimum amplitude, the minimum energy, depending on which units you use, contained per pixel. So we figure out what the minimum and the maximum is, and then we just modify our plotting range here. And this is what you get. For, I think this is right? So loading levels to data. You can do the same for Hanford, and in fact, this is a hands-on session, so you should actually do this for Hanford yourself and see what the differences are between the two detectors. So a power spectral density gives you essentially the behavior for a moment in time, more or less, because that's what we're analyzing. But here we're looking at a spectrogram which tells you what is the evolution of the sensitivity across your domain as time evolves, because our detectors are not, they're not static. Things are happening in there, the noise is changing. Now, in this particular case, it's actually pretty, pretty well behaved over that time range.
Sorry, I'm sorry, where did you choose this data to be done for?
At the very point, so when we loaded the data here, I called my time series L data and H data,
Oh,
right? And then I just chose here to plot the spectrogram of the L data. You can do the same for H. I should point out here, so I have particularly chosen that I wanted to have the spectrogram over the entire stretch of data. You don't have to do that. You could just define, a smaller range of data that you would like to generate a spectrogram for. I've chosen the overlap of these segments here. So how much overlap do I want when I do my windowing? In this particular case, it's a 50% overlap. You could choose a lower one, a larger one. And I would suggest play around with that and see what the impact is on the spectrum. And you can do different types of windows. So how do you actually choose, the tapering, the edging off to 0, smoothly to 0, there are different options for you. And these are standard functions in the signal data processing piping package in SAIFR. But there's nothing specific here in that sense. Features to point out here, I think if you squint, you can see that there is quite a bit of excess at 60 Hertz, which is the US power line, which you can see, and you can see access of higher harmonics of that power line as well.
So what is this uptime of the closing? That's also described.
The green one here, whatever this is, 600. I think this is actually a value mode, if I'm not mistaken, of one of the suspensions, right? So Aaron mentioned yesterday that the mirrors, our end test masses, are suspended on these 4-stage pendulum to reduce seismic motion. But of course, every pendulum has a resonance frequency. And so it's not alien.
The white line at like 35 hertz.
Is the lower harmonic, I believe, of the color, but not mistaken. So the two thirds or something like that.
When you say that in harmful,
Sorry?
not harmful. So,
Which one is not very many? No, that one.
The very bright one here is not
Yeah,
open.
that. But if it's like
the geometry side.
The geometry is not different. But
In this area, it could have been the calibration.
it could be a
lines,
calibration
but I'm
lane
not
as well. I'm also not sure. Aaron mentioned that our detector output has to be calibrated, like with every experiment. So specific lanes are also used for calibration. So it could be that this is a p-cal line, for example. I'm not 100% sure. I don't know, Colin, do you remember more specifically?
Sorry.
The p-cal values line, at which frequencies calibration is done.
at what frequencies?
Yeah.
And roughly was once plus.
The other thing, I guess, to see is you can clearly see this rumbling here, right? So if you were to transform those frequencies, right, in your head, this is low frequency noise here, you can see below 20 hertz. That's quite an access here. And that is exactly what we saw in the XD. It was coming from what you saw yesterday when Aaron was showing the different noise sources which contribute to this particular shape of the strain noise that we observe. So at low frequencies here, right, we have a lot of access because Aaron was describing the various contributions from the Newtonian gradient noise and the static noise due to the Earth. So to beat this, you have to go into space or underground and find a really quiet place. Maybe you can beat it down to like 3 hertz or something like that. So that's what people are looking into for the 3rd generation.
Caverns this point.
Yeah.
And this everything on the wall.
Even
They are.
Your x-axis is in how many bits? Or how many points?
The x-axis. Good question. You should be able to find it out. So I haven't changed the resolution of the data, so it will be the resolution that we had from reading in the data, which was this dt. So 10⁻⁴ is the dt space.
So if your time ranges are very small, then the frequency uncertainties will be large. So you have a frequency versus time plot.
Yeah, frequency versus time plot. So what you're averaging, right? Because we're doing this over time. But yes, you're reducing your uncertainty. Okay, everybody got a spectrogram and kind of get some idea of what it means. But of course, we have chosen data around 150914, and then we're looking at the spectrogram, right? And everybody's like, well, it's 150914, right? All I kind of see is this sort of nicely behaved noise that doesn't change too much over that stretch of 6 seconds. But there clearly was a gravitation. There was a pretty loud gravitation in there, signal to noise ratio of about 25, right? So how can we see that? Well, if you want to kind of tickle out specific features in the spectrogram, the different ways of visualizing this, and the one that is commonly used in the calibration is a Q-transform, which is a specific type of method of producing a transformation that is particularly good at essentially picking out features that are compact in the time frequency distribution. So if you look at the kind of zoom in here, right? So here we had like the full range, which goes up to like almost 2 kilohertz. But we know that compact binary coalescent signals, depending on the mass of the signal, are actually spanning a very, very small range of time, frequency, space, so to say, right? So the domain is actually pretty compact. If you go to relatively high mass signals, you might remember 17017, about a neutron star that had a much more extended signal because we have a long inspiral due to the low mass of the signal. And the Q-transform is very good, essentially, at picking out things that have a compact domain in this time frequency timing space. The Q and the Q transform stands for the ratio between the central frequency of the bin that you're choosing, or think of it like the segment, and the width, the uncertainty, essentially, so the bandwidth that is covered around that. So this is what this Q factor means. And what's interesting here is in this particular plot, we don't use a fixed Q. You could say, okay, I can just, have an equal sort of tiling of this space, right? So I have like nice equal tiles in my frequency time space, like you would do with a short Fourier transform. But that will essentially give you what's happened on the page above, right? So it will be very uniform. It will not be amenable to picking out specific features that have a certain kind of evolution. So what we do with this Q transform is we change how much resolution we put in these bins depending on where you are. So at low frequencies, we essentially keep the bins as you would normally. But as you progress to higher and higher frequencies, we choose differently sized bins. So let's say we have these ones here, let's make them twice as big. And then we're going to go for these ones even more. So this is what's happening here essentially. You can think about this as a natural filter where you have a logarithmically spaced frequency tiling in your frequency. So that's kind of what's happening here. And if you do that, you get this beautiful picture that is really, really pulling out those very specific chirp-like features that we expect for a compact binary coalescence. It was initially actually introduced not really for CDCs, but for burst signals. So burst signals were these minimally modeled signal kind of types of transients, let's put it that way, that Maria mentioned as well on Monday. But it is, essentially a high mass BBH is a burst signal, more or less, in terms of its morphology. Ricardo had a comment or a question? No?
Can you say more about the Q transform? Just.
If anybody has a deeper understanding of the Q transform.
No, for instance, why people don't, is it better than wavelets? People study wavelets?
It is actually closely related to using the wavelets.
I think it might be a particular selection of wavelet transform.
Yeah.
In a sense. Because they're very similar in the sense that they do the same logarithmic scaling.
But in the wavelets, you're assuming some part of the function. Here, you're just trying to say, it's being going to have relatively similar set of
So here you don't, so if you have the varying Q, which is what we use, you don't assume the same amount of energy per bin, actually. So you can have a constant Q where you do exactly that. You tile the space such that the energy content is the same in each tile that you're choosing. Here we are not doing that. You can do that as well. I think the main difference is, the way I think about it, wavelet transform is you're essentially taking this 2D space and you're selecting basis vectors, right? That's how I think about it. And there are essentially different types of basis vectors you can select.
Yes, we see essentially here that the signal kind of stops at 0.42. For the other detector, it's more like at 0.435. This is simply because they see the signal at different times.
Exactly. My gravitational waves travel at the speed of light. Depending on the location in the sky, it will be seen by one detector earlier than the other, and the difference would exactly be the light travel time between the two detectors. Absolutely. And if you had Virgo as well, you'd see another different time then, right?
This plot is enough for us to conclude that there may be an event before we do any match filtering.
No, it's the other way around. Right, so we do the match filtering, we don't, the spectrogram is normally something we produce after the fact because it's a very nice diagnostics tool to visualize, but the match filtering is the first step. And so there we collect these SNR time series, so where you get spikes in the time series. You scan your data continuously for this template bank that Aaron was mentioning yesterday, and you'll get essentially distributions of SNR time series. And whenever there is a peak that passes a certain threshold, and how you define that threshold is a tricky question, then we would essentially group this together, say this is a candidate. And if you look at our internal kind of pages, we will also have automatically generated spectrograms to look at that.
But that would be true for waveform that you know of, and you have the ability to do much better with spec too. So if it's just give you a walking thing that you've never seen before, would you?
So for
take
the
this-
So the burst search folks, right, they essentially use spectrograms, but it's not like they're like looking at a spectrogram to make a decision, right? So you can think about this as an energy tailing, and what they're looking at is really this kind of, they use the Q transform as well, more or less under the hood, right? To get a grouping of the energy tailing, but if it has a specific, if it follows a specific way of how the energy evolves, then the burst search will essentially ring off as, hey, I have an interesting candidate.
But it's the same situation where they're applying an algorithm to every stretch of data. So they're marching this along, creating energy maps, doing the calculation on them, and then trying to compare at a given amount of data, how significant is that particular energy pattern versus the background energy patterns, right? So you still have to have some automated system to compare. How good looking is this compared to noise background? Because glitches can sometimes look not, they'll never look this good, but they can look reasonably like gravitational.
And especially the more you go to the unmodeled plants where you the burst time, you will lose more and more of that chirpy shape, right? It will become more and more the final part here. So kind of like almost straight looking spikes in this time frequency plane. And that is also a characteristic of some of these, you know, transients, non-astrophysical transients that we see, the data that we refer to in the charges, which is calling it a comment or something.
Yeah, I just want to mention too that these graphs, they really are mostly used as a sanity check to see if it looks like a glitch or not. Because there are, like you can clearly see the chirp here because it's finding a black hole, but for like binary neutron stars that are more low mass where the energy is smeared out over hundreds of seconds, you could actually have a 5 sigma event. You won't actually see anything in these sort of plots because just the energy is so spread out. So it's not that you have to see this to verify that it's a real event. It's more like, does this really look more like a glitch than an event? And if it does look more like a glitch, then you start digging through your statistics and try to understand what kind of problem.
Yeah, this is more to show in seminars.
Yeah, it's more the pretty plot that you stick in talks to that. You're very lucky that the first detected event was one that you could see it, so it was kind of really. But yeah,
It's still the highest national BBH that we saw.
No,
No, it's not.
there were ones in 03 that were higher.
There were 2 already.
But just to prove on the other side, I mean, as people go crazy with potential sources, we have cases where there is an aperture, and the signal evolves in the opposite way. Prove that. So I think that if it's sufficiently loud, we might end up to take a look at it before we're the same.
to date though, there hasn't been. I don't know about before, but there hasn't been any events that were detected by the burst group that were not detected by the CDC.
Sure, but well, I don't think these events, I don't think you're going to be able to get it. They just goes- Yeah, it's pricing things like. What I see in all the simple nature of EDD.
But I just quickly wanted to point out what Colin was just saying, right? And also the dangers with like the long signals, or because our detectors are not perfectly stable, right? And so this is the data for 2017 in like Olympics. Again, you can see the Q transform here of the spectrum. And you can see this massive spike that goes through a reasonably clear looking chirp, but this is exactly what Colin was saying, right? So the chirp is much fainter than what you've seen before because it spends more time, so you have the accumulation of the same type of energy, you know, over a much longer stretch of data, but it's still reasonably clear here. I think everybody, if you squint, can see it. But then you've got this huge excess power that's like right there going through your chirp signal here. And you know, if you didn't look at the low frequency content, that final part here looks very similar actually to what we see for 1514 at the final stages there, right? So this is where the trickiness comes in of distinguishing between a real signal and an astrophysical and a non-astrophysical signal if the morphology kind of becomes very similar at this frequency. That we have different types of glitches as a whole. So if you are interested in glitches, you can participate in the citizen science program called Gravitational. where you can look at gravitational wave data and classify glitches, which helps the underlying machine learning algorithm to perform better automatic classification. Oh yeah, go for it.
No, okay. The other thing is you obviously can't shield a gravitational wave detector from gravitational waves, and this means that we have a network and you look at coherence between detectors. The seasoning in one detector has a certain shape, you can see that in the other detectors, so you can then check. I mean, normally. So the mathematical set is asked for a different sense. We have coherence sets with line data, and just other methods you can use that for the signals itself. This is detectors.
Yeah, I didn't have time to talk about it. All the stuff I talked about was focused on if you have a single detector, how do you try to detect a signal in it? But if you have two detectors, obviously the most natural thing is to enforce some sort of consistency between what you're seeing in the two detectors within a certain range of times consistent with light travel times from different arrival directions. And that, in people's minds, actually is one of the core ways we search for gravitational waves. But in fact, I think the thing that people don't appreciate is that while in the earlier runs, we enforced coherence between the two detectors more strongly, in the later runs now, we make single detector claims of detection all the time.
That's largely because we now have a sense for the signal population.
Exactly.
We're actually able to have the proper probability of signal, not just the probability of noise.
Yeah.
So why would the other detector miss it?
It could be down.
Okay.
You know, it could just be a low signal to noise ratio signal that might just, you know, if the detectors are not equally sensitive, it could just drop below the threshold in one detector, but it's just above the threshold in the one that is more sensitive. So it's, you know, there could be many reasons for that. Anyway, I realize we are rapidly running out of
Can I
time.
add on this point?
Yeah.
So the two LIGO detector are related the same way, so that they should see roughly the same signal noise ratio for a given event. But Virgo is not. So if you have a double coincidence with the two LIGO, then it means that the source was well oriented with respect to them. So Virgo is bound most of the cases to have a lower scenario. On the top of having a worse noise, but we always have a lower scenario on coincidence in LIGO, just because coincidence in LIGO automatically picks better orientation for LIGO, which is not another reason. No, but it's good once you have more than two, it's good to have different orientations, because then you can do better cross checks, and also you can cover the blind spots of LIGO. But but okay, the third detector is always bound to have a lower scenario on the double coincidence of LIGO.
And the polarization problem, which you don't get if you have cool. Okay, we running rapidly out of time. I'm not sure people are so interested in PhDs, but just a quick thing here. We have just generated a spectrogram. So of course we can generate the proud spectral density for that, which is the thing that we're probably most used to looking at. Again, GW pi has a direct function for you. It does exactly what Aaron was describing yesterday. So you can look at the source code. But here you can see it for the stretch of data. And we can see we do have obviously quite a variance there, but pretty roughly similar performance in this particular case. You notice this weird, strange turnover point at the end here, which is a data artifact. So of the downsampling, and the way the going to roll on and roll off is being chosen. So how to, you know, choose how to taper the data at the end in the time domain. So this is not something we would normally use, of course, in the analysis here. So you stop the analysis in this case at 1024 hertz. Nice powers of 2 to make FFTs. Okay, but I think most of you are interested in waveforms, so let's go and look at waveforms. So as I said, we'll be using for this tutorial ICTP to access the waveform code. You don't have to do that. You can directly access last simulation, which is where all of these particular waveforms are coded up here. So we load the waveforms package in PyCPC and a bunch of handy functions. In particular, the first one is, of course, what waveforms are actually available? What can I even, what's coded out, what can I use? Straight out of the box. So you can use these two functions here, TD approximate and FD approximate, to print on screen in this particular case, which approximates are available in the time domain. So these are time domain approximates, or in the frequency domain. They're not necessarily the same. For some of them it is because developers have made the effort of implementing automatically to generate them in the inverse domain. Some haven't done that. But yeah, you can look through this. There's like, it's a long list of paper models that you can pick, keep scrolling. So there's many of them. Some of those will look familiar, hopefully, by now, right at the very beginning. So various post-Newtonian approximants. So these are the Taylor approximants, or the spin Taylor approximants if you include precession of the spins. We have the norm models, various iterations of the norm models. So Gary was mentioning the latest iteration is IMR phenom X. If you want to use your latest phenom model, that's included here. And then I put a little star here because there are various flavors of that. XAS for just the aligned space 2-2 mode, XP for the 2-2 processing mode, CHM for all together. So there are various variations here. I think in a hands-on session you should just play around with that and see how the waveforms are different depending on the type of business. And then there's also a bunch of different EUV approximants that you can access in here. So yeah, again, just have a look and play. Anything that has a sort of T or title somewhere in this obviously includes title information. We haven't talked about neutron stars, but obviously we're also observing mixed binaries or binaries consistent to neutron stars. So you want waveforms that include at least FFPN title effects. So there are some Taylor versions here, but then there's also phenomenological waveform models and models that include technology. And then let's generate a waveform. So the base function here that we're using is getTD waveform. If you are familiar with IPython, so if you type getTD waveform question mark, you'll get information on how to actually use that function. So we can just do that. And I will pop off a little window on the side here that will tell us what the inputs are and what the outputs are of this function, because the PyCDC folks have done a good job of writing documentation. So you can see all the input parameters here. You put the masses of your black holes, in this case, the various spin parameters. If you had tides, the tidal parameters, there are some eccentric waveform models, so you specify the eccentricity. There are various higher order tidal information that some waveform models include, especially the EUV waveform model. There are options to modify these waveforms with these generic test of general relativity tests that were mentioned yesterday by Louise briefly. Then we have extrinsic parameters like how far away is that binary, the inclination, various other quantities relating to the orientation of the orbit relative to the observer, the lower cutoff frequency, so where do you want to actually start generating your waveform from. If you have a processing system, spin orientation evolves, which means you need to specify the spins at a specific reference frequency or time. So that's contained in this bracket parameter here. For post-Newtonian models, you might want to take your latest and greatest spin Taylor model, but you're interested in only going, say, up to 2 pn in the phase or 1.5 pn in the spin. You can specify this as well, and you will discard all the higher order terms in the series, and so on and so forth. If you have high order modes models, you can choose the number of modes you want to include. Don't have to do all of them, especially if you want to test, for example, how it impacts your parameter estimation. You can just sub-select the number of modes you want to include. You can also load numerical relativity data. So we have part of our infrastructure that we can use a data frame that contains a numerical relativity data set, and you can just output that waveform in your standard lab format, and you can use it for data analysis, for example. So there's many options, and this is the simplest example here. Here we're using a time domain SUV model V4, so that's not the latest, but the previous incarnation. And I've just chosen here an equal mass binary. Remember, this is a line spin, no precession here, so we only need to specify the Z components. So the components align or anti-align with the orbit angular momentum of the binary, the masses. I chose a particular time here for sampling and zero inclination, meaning it's based on. And the lower frequency, I decided I want to generate this from 20 Hertz.
So these are mostly analytical waveforms, right?
Yep.
Okay, so the one generated by numerical
You need a data set that actually contains it. So within the collaboration, we have the data products available to us. I don't think the GLCNR catalog is public, or is it? It is public, you need to download it. It's quite a big chunk of the data repository.
So that's why you can tune the parameters as much as you want, because otherwise, like.
That's right. If you were to choose a numerical relativity waveform that you want to plot, you'd be constrained
Yeah.
by what mass ratio was the simulation actually run it. You could still scale it, of course, with the total mass, because all of them are scaled to 1, but it will determine the length of your waveform in frequency space, right?
Okay.
So numerical relativity waveform have a fixed length, depending on what initial separation was chosen to generate the waveform. And then depending on the mass you choose, that translates into a specific F lower. So that's the only thing. So you know, in terms of what you can do with it.
Here there are almost those things.
That's right.
Yeah.
I mean, in this case, if you try to evaluate it with processing spin, it will throw an error because this is a non-processing model. So those are the constraints on the physics that's included in the model here. I would say more than in terms of you can evaluate it. Now, the big caveat is, of course, you can call this model outside its official validity range. It might throw an error depending on the waveform model. It might only throw a warning. So, you know, we use NR information to calibrate. Beyond that, there's a big void because we have nothing to compare against, right? And so there you know, it's up to you how much you trust that model. So in the reviews, what we normally check is smoothness as you go into the extrapolation region, so you don't get something super crazy. But there's no guarantee that it's actually physically correct, right? Right. So, what you get out of this is actually I didn't say, plus and cross polarizations. Because we remember what our detector then actually sees is the projection, right, of these onto the detectors, right? And I just showed that, you know, pluses and crosses just with the acoustics and the limitation. So here you get your H. And then we can plot the waveform. Et voila. There you have the two polarizations, and we should play around with this. We can zoom in at the merger, and we do see the nice shift by pi over 4 between the two polarizations as we expect. You can do the same now with the frequency domain model. So in this case, again, align spin 2-2 model XAS, so that's why I put a little star here. I haven't changed the parameters, they're the same. You will notice what we now need to specify, since we're generating a waveform in a frequency domain rather than the time sampling as opposed to frequency sampling. In your array that you're putting out, at the end of the day, these are just Python arrays, right? Which is what we do. And voila, if you're not used to looking at a waveform in the frequency domain, which nobody ever does, that's what the amplitude looks like. And in this case, you'll also notice that they have the same between the cross, because they essentially correspond just to the 2-2 and the 2-2 mode, and there's a symmetry in the aligned spin. That symmetry does not exist. It's not necessarily always captured, but from a fundamental point of view. Now, what you also notice is that sharp turn on, right? Because we have specified a low cut of frequency. So you've really got a discontinuity here because you've decided I'm generating my waveform from 20 Hertz, right? So below 20 Hertz, this array doesn't exist, right? So if you think about it now going into the time domain, you again have to be careful when you do an inverse FFT. So we normally have to pad the data to have to write a array length in order to be compatible with powers of 2 for the FFT. And we also normally taper in order to have a smooth turn on to avoid edge effects when you do both ways, your IFT or your FFT. Okay, so data condition is taken care of in the analysis, but just again, something to keep in mind. And it's actually really, really
on the merger then, how do I, like in the waveform is very clear on the merger.
Yeah. The merger happens at high frequency, right? So this is your in spiral portion. Then you've got your merger peak here, and then you've got your ring down, which in the log plot is a straight line because you have an exponential decay in the ring down.
Wow.
Good question. I'm so used to looking at this, but yeah, I've never looked at this. Absolutely. It's a very classic methodology for a CDC. And then just for playing around, I wanted to give you an example where we now include precession. So we now allow arbitrary orientation of the spin in the source frame of the file and generate that here. I've just picked something that where precession is very obvious. Okay. So I've tweak more parameters here than just changing a single one. So you can see the main characteristics is we now have to pass all the 6 main components, because that's what causes precession and misalignments. Here we're using a Cartesian decomposition. And then I've also increased the mass ratio just because the effect gets more pronounced when you increase the mass ratio. Or decrease, I guess, in the UT language, depending on how you define UQ. And then again, this is a frequency domain model, so just showing you here the H plus and the H cross, again here, for this particular waveform model, you can see that the morphology is very, very different. You still have the in-spiral path. You still have your merge, of course, and you still have your standard ring down. But you can see many, many more features of the amplitude down. Because once we have precession, we get these really strong phase and amplitude modulations, depending really on the type of precession you have included, so to say, and that gives these very, very characteristic, dips in the frequency. You get a maximum every time the orbital angular momentum of your processing orbit crosses your line of sight. That's when you receive most of the energy, so you get a peak. But then as it moves away from you, the energy that you're actually receiving will go down. So you get this really nice modulated behavior. Now for this from XP model, XP model, the developers have gone through the effort of including a way of generating it also in the time domain, so the data conditioning is automatically done for you. You don't have to worry about it. And this is what this exact waveform looks in the time domain. Here we're looking again at this H plus and H cross, but now the time domain. And as opposed to the EOB waveform I've shown you before, which we directly generated in the time domain, you can see now we have a kind of smooth, slow turn on. Let me go back to this one here, where it just started, right? Which is like, you start, and that's it, right? And here we can now see we have the smooth turn. And that's kind of visualizing what I tried to kind of awkwardly say before is we have taken something, the frequency domain that had sharp edges. That will give you bad effects when you transform into the time domain. So we have to do some data conditioning where we pad the time, the frequency series in this case, and add a window, an appropriate window. But the consequence of that is that you then in the time domain get this turn on.
So if you wanted to have like an H instead of the 2 separate, you
generate the appropriate antenna patterns, which are essentially just coefficients, right? So the antenna patterns are actually about the geometry of the detectors, and they depend on the right ascension, the declination, and the polarization angle, because that is essentially codes the relative orientation and will tell you how sensitive your detector, because it's not only sensitive, it has, as Ricardo was mentioning, some blind spots and some peaks. So you evaluate these functions, they're coded up. You can directly call them. You get 2 numbers here, and then essentially you just convolve them with each other. So what this normally does, it makes it even more modulated, because these are assigning consent functions. And the change of the GPS time, of course, as the other.
And those functions are fully provided for you.
Yeah. You don't have to code them up. You can call them in PyCDC. I think they're just called detector pattern. So we can look it up. They are fully there. I can add it in and update you if you guys want to see that. Okay, I know we are way over time, but do people want to hang around for another 15 minutes? Look at parameter estimation. Okay, so this is just giving you a flavor. Go play around, manipulate, change the parameters, see what happens to the signal, and I'll look up the function name, and then you can also project it onto the detector pattern and actually kind of construct the HT. Okay, final example, parameter estimation. So we kind of have all ingredients. Now we have waveforms, we have a power spectral density. So we are more or less set to actually analyze and figure out what was in the data. Right, so we use this Dolby package, which again is a Python library that is very accessible, easily manipulated if you want to do your own things, so to say, and we'll use it to set up our inference problem, which is exactly the problem that Aaron was describing before. Remember, we had the specific likelihood, which was the data minus the template, and that will, of course, under the Gaussian hypothesis, which is what we were using. We don't have to worry about this. This object is created in Dolby for you. But what we have to feed in is the data that we actually want to analyze. power spectral density that goes with the data, because remember, the inner product was weighted by the noise. And then, of course, we have to choose what model are we going to use to compare against the data. So these are the three main ingredients, essentially, that we have to do. So in building, this is more or less here just building structural parts. But what we basically need to do is, first of all, we need to choose what detector network we're going to analyze. 150914, so we're going to use Hanford and Livingston. We don't have good data, right? Okay, so we initialize Hanford and Livingston. Is what we're going to do. Okay. No, that's just
I need to get the charger.
perfect. Then we need to define how much data we actually want to analyze. Remember in the example before, we downloaded 16 seconds of data, but then we looked at the Q transform and that signal was like super, super short, right? So for the actual parameter estimation, there's no need for us to analyze those 16 seconds of data. We will need a long stretch of data to generate the PSD using the method that Aaron described yesterday. But to actually then perform the likelihood evaluation, so the integral, we will use just the data around the signal that we want to analyze. So we define this, so we want to define how much after the peak stream of data do we want to keep. So we choose 2 seconds here, which is the default in our analysis. You can change that, but it's the default we use. In this particular signal, we are being conservative. We use a stretch of 4 seconds, essentially, in total. And we start the analysis such that the peak stream, the GPS time of the associated event is essentially centered around the data stream. And then we use the same as before. We use the GW pi time series to fetch the data. But now we just fetch this small part. Okay.
For example, right, is
the sample rate in this case is provided to us actually by the data frame. The data frame is sampled at 4 kilohertz. That we're downloading from us. So the original output is 16 kilohertz, but the data we release to the public is then sampled.
there, there's variables. I choose.
You can choose a different one, and I think it automatically resamples for you if you want to choose a different one. But I haven't done that. I've just gone with what's provided to us because for this event it's actually sufficient. For the folks who know something about kind of signal processing, they will realize that because of Nyquist theorem, the maximum frequency that is actually resolved in something that's sampled at 4 kilohertz is 2 kilohertz. If you think back at our nice Q transform, I don't know if anybody looked at the upper limit of the frequency, but that was well below 2 kilohertz, right? So 150914 had a ring down frequency of, I don't know, 200 something, right? So we don't need to worry about that. If you had a long duration signal, like 170817, well, binary neutron stars merge at the kilohertz regime, you'll have to be careful about the sampling rate you choose in order to make sure that the maximum frequency you want to do your analysis up to is actually contained in your resolution. Okay, you don't need to plot this again. It's essentially just the same plotting routine as before, but now just those, few seconds that we're now actually analyzing. And I don't know if I look at this, I don't necessarily see gravitational wave in there. See a lot of wiggles, but that's about it. So we have initialized our detector objects, we have downloaded our data, and now we just tell this is just pure from a Pythonic way of how the structure is set up. We now tell it, okay, this detector network and this is the associated string, so we just initialize it appropriately. And then we need the power spectral density. Remember, our match, which is effectively what we do at the likelihood integral, had a 1 over Sn of n in there. So we need to construct this amplitude spectral density, and we'll be using, in this case, the Welsh method that Aaron was introducing yesterday, which was to take a long stretch of data and then chunk it up into smaller stretches of data, computing the power distribution as a function of frequency in each of those average everything. That's kind of what we're going to be doing. And here we choose 32 times the duration, which is a typical method when you do what we call these kind of all-source PSD estimation, which is not in practice what we actually use. We use a different way of calculating the power spectral density, but for all intents and purposes, this is sufficient.
So where does that number come from?
32. Well, it's kind of the 1496, right, divided by 120 is what we said yesterday, right?
Oh.
So sort of thing. I think it's something that, I don't know if there's a deep fundamental reason. I don't, is there a deep fundamental reason for the particular combination?
I don't know how 32 gets chosen, but the more segments you use, the better, the less variance, right, in your estimate. You do the average. So more segments means you're going to get a more representative PSD. But if you use too many segments, then you have to grab a segment of data that's maybe hours long, and by then the PSD may have fluctuated on some level. So someone must have decided this is a good trade-off.
Anyway, it has to be power of 2 because the
Yeah,
FT, the FFT is fast.
But it could be
I
16.
like 16.
Exactly. Okay, and then now with the data, we actually compute the PSD. So this is implementing here Welch's method, the one that Aaron described yesterday. You can see here the window specification that's been chosen here, and there's a parameter called the PSD alpha. I don't know if folks are familiar with the 2P window. A 2P window looks kind of like this. It's got like a zeroing, then it's got a wing, then it's got a smooth top. So it's kind of like a smooth top hat, where you smooth out the edges. And of course, you can change the steepness, right, of that transition here. So how smooth is your edge? How steep is it? You know, how long is the incline? And that's controlled by this particular parameter. And I've not chosen anything special here. This is a standard one that's been chosen. And then again, the next step is just, okay, we have this object, this interferometer object, which was initialized, and we need to fill it in with information. We've provided the data information already. Now we're going to provide the power spectral density information. So it's just a way of storing that information in the object. And then we can also plot the state that we have just created. And in blue, you can actually see the straight data that we downloaded here, plotted in frequency domain, and overlaid in orange, you can see the power spectral density that we have just created with this particular method above. Sorry, I should say the amplitude spectral density. So we have the noise, we have the data. Next step, Bayes' theorem. We need what we need. So we're interested in the probability of some parameters given the data array, and that's proportional to the likelihood of the data given some parameters times the prime of the parameters. So we want to set up a prior. Now, there's many different ways of how you can do that and what priors you choose depending on your analysis. This one is a very simple example here. So the general way of how to do this in Build is you initialize dictionary, a Python object here, which you populate with the various parameters that are required. And Aaron mentioned, and I think Maria mentioned, Aaron as well, like normally that would be about 15 parameters for your generic analysis. That includes spin precession, but not eccentricity and no tides. That number will change if you include, for example, eccentricity, if you include tides, etc. So in this case, this is a binary black hole analysis, a very simplified one. So we fill it up our prior with some, guesses, I would say, on the mass parameters. In this particular case, we will be choosing actually the chirp mass and the mass ratio rather than mass 1 and mass 2, the component masses, because it is more efficient for sampling. Then we have the phase parameter here, the time, sampling also over the time, as Aaron was mentioning, right? Different wafer miles will give you slightly different peaks, slightly different times, and that will be different to what was found based on the template in your original search. Spin parameters, now you'll note here, spin parameterization and the parameter estimation that we use is in spherical coordinates, not in Cartesian coordinates, as we did before in the waveform generator. So we need to transform coordinates here, which is not a big problem. It's done a little bit for you, so you don't have to worry about it. Right essential declination, so the position in the sky, inclination, which is called theta gn here, the polarization angle, and the luminosity distance. So these are mass, spin, and all the extrinsic parameters here. Now you'll notice not all of them are actual distributions, right? So some parameters here have explicit values. So we're kind of cheating. We're reducing the dimensionality of our analysis here, which is not advised in a real analysis. But in order for this to finish in 10 minutes on your computer, that's what we're going to do. We reduce the dimensionality. We also have very narrow priors here. As you can see, we're only sampling between mass ratio 1 and 2, and a very narrow trap mass prior here that we draw our lupus from. We have the phase as the standard one, which is from 0 to 2 pi, and then quite a small time prior, which is pretty normal because the time resolution is normal. But very good, it's even better for long durations. And then we fix everything else essentially, except for the luminosity distance. And here we choose a power law. You could choose very different priors, of course. Power law is what we normally do in analysis, but you could, for example, use a distribution in co-moving volume or something like that. And we are very agnostic here. I should also mention we use uniform priors here. Again, you could choose something different, right? Choose a Gaussian prior. Depending on whatever your prior knowledge is of what you're analyzing, you want to add it to your prior. We're normally very agnostic in our choices. But again, depends on the analysis you want to conduct. And then we have essentially almost everything. The only ingredient that's missing now when we compute the likelihood, remember we were actually looking at the likelihood where we were computing d minus h of some theta. So we need a model waveform here. We need some guesses of what this h is that's contained in our data, and that's where the waveforms come in. And in this particular case, we choose Eimer-Phenom XP. You could choose any of the other approximants, more or less any one. I wouldn't bet that all of them are going to work, but you could choose several others in that list that we saw before. And the rest is essentially just a little bit of syntax part. And then the key point is we can now initialize the likelihood object, which you don't have to code up, it will be already for you. So it's coded up the right likelihood that Aaron wrote on the board yesterday. And we're passing in our parameters, which contain the data and the power spectral density. We pass in our waveform models, our template for the waveform generator object, and we pass in our file. And then we can choose to further speed up our analysis by using a trick of marginalization, which is integrating out some of these parameters rather than sampling over them and then reconstructing them in post-processing. And in this particular case, we choose that for time-phase and distance marginalization, where this can be done. Analytically, again, this is here to speed up the analysis. It's not necessarily something you always want to do or can do. It depends on the problem you're tackling. So, of course, I didn't finish the trial, so it's sort of thing. And then it's not sampling.
Sorry, one question, like on the luminosity distance, that's the only parameter that's not kind of the model of the waveform sense from the kind of.
Yeah. So it is in the waveform generator, but of course, when you model it, you don't care about it. It's the same for the total mass, right? So, I mean, when you model the waveforms, you are, because everything, as long as you don't have tides, everything scales, right? So it's just all scaled to 1, and then you rescale it to whatever the total mass is you have. So from, if you actually do your model, when you integrate it into the waveform generator, all we do is we just rescale it then by the total mass and the distance that you want, because it's just a 1/dl prefactor in front of the entire string. It's the same with the inclination, right? So the inclination is not an intrinsic model parameter. So intrinsically in the model, all that matters is essentially the mass ratio and the space.
That's right. Just to say, this is doing a pre-computation. You're not yet.
That's right. Sorry, we're not yet sampling. I'm sorry, we're not. So here we are doing this pre-computation in order to apply this trick of not actually having to sum over the distance when we do the problem. That should be reasonably. My computer's been very slow. I don't know.
It's not the first on my computer.
Others might be.
I'm almost done.
2 minutes. All right. It's just a look at the table, yeah. The sampling for me took 7 minutes yesterday when I tested it. And apparently on the open data workshop, it only took 1 minute and 10 seconds. I was like, wow, what kind of coordinate data?
What's that? Maybe just the next.
That's dynasty, yeah.
Mine took 6 minutes. Yeah.
Okay, almost there, 98%. Sorry, this was the preconditioning step. I apologize. And now we are ready to sample. We have everything to call the sampler, and if you want to use Bilby, it's the simple command of run sampler. And then we pass in now our likelihood object, the prior object, and then we essentially specify how we want to do the sampling. So as I mentioned before, you can choose a custom sampler if you want to write your own one to solve your Monte Carlo problem. Or you can use one of the many packages that exist and are already either hooked up, or you can hook it up yourself to the Bilby interface. In this case, we're using Dynasty, which is the default sampler now that we're using, not written by the collaboration, right? This is by Josh Spiegel, and Home Talbot, I should say, has made some specific modifications that make it more efficient for the specific gravitational wave problem measures. This is just some naming conventions. So in principle, there will be some data obviously created, samples, hopefully, because that's what we're after in the end. So you name your output directory, a label for what the job is being called. These conversion functions take, for example, care of this conversion between Cartesian components and spherical components in your spin parametrization. The number of walkers, the argument here is n-line. So Aaron was mentioning yesterday when he illustrated the Metropolis Hastings algorithm, right, that you seed your analysis initially, and then these walkers explore the likelihood surface. You can choose how many you want. 250 is not what we would normally use. We would use it large enough in order to make sure that we're really exploring the full space. And then the D-log set, because we use a nested sampling here, there's a stoppage criterion, which is based on the change of the evidence as you're exploring the likelihood surface with your walkers. And here we choose a very rough bound of 1. Normally, this would be an order of magnitude lower in our standard analysis. And then we run it. And now we'll see who's got the fastest scores. So it sets up, prints some info to the screen here where it tells you what's being used under the hood. That prints the prior that we have fed in, so you can sanity check that it's really using the one you wanted to use. And then telling you also the kind of parameters you have passed to the samples and the sampler arguments. They are all the ones you haven't specified, it just assumes the default values that are in the code. And then it starts generating the initial points from the prior, so seeding your walkers. And then we'll actually start sampling eventually. That will be 4.
Run. My computer here on.
So yours done already? No, it's fine. I mean, it's okay. I think we can read because I don't know if everybody's already done. So what comes out of this when you're done? The object you're after are, of course, the posterior samples, right? So what are the best fitting parameters that describe the signal hidden in the data that we have analyzed based on the prior, the sample settings I've used, and the wave model that I have used. And we have used very, loose settings here. So what would you expect your posteriors to look like, your posterior distributions? Question for the audience before everybody falls asleep. Yeah, in the ideal case, it would look nice and smooth and Gaussian, of course. You will see, based on what we have done here, you'll get very ratty distributions that are, not really nice and smooth and Gaussian. And that's, in this particular analysis, definitely an artifact of the fact that we are not really in a regime where our distributions have converged to the true value. Right? We have chosen a very small number of life points to walk us to actually explore that parameter space. We have a very loose change of the evidence criterion to stop our sampling, right? So, I mean, it's evident that we will not have very truly converged to what we think is the asymptotically correct result. To do this, the analysis would take significantly longer, at least with our methods. There are other methods out there which, might be a bit faster, but may not necessarily be as converged. So I'll leave that, if you look at various outputs, you can judge for yourself. But what you really get out here at the end of the day in terms of data product are panel data frames, and then you can do You can plot the one-dimensional posteriors. You can also plot, of course, the 2D-dimensional posteriors between different parameters that you're interested in, which can highlight some of the correlations that we expect between parameters, for example, or maybe reveal correlations that you haven't thought of before, but then discover as you do the full n-dimensional analysis here. You can compute things like the median, the mean, the 90%, credible intervals, depending on what you are after. And your analysis, and ultimately do some awesome astrophysics, SFGR, whatever you want to do, because as Aaron highlighted yesterday, this is probably the main data product that people who want to do the science afterwards are after. And again, well, this is sampling, and my computer's clearly very slow. You can play around with all of this here, and you can change your plan. And I would really encourage you to just play around to develop a better understanding and feeling for these things, right? And you can run I initially had here a 170817, which is more like, oh yeah, you guys should repeat all of this and now take a bite on your stuff and see what are the differences, right? It will be quite illuminating. Well, if you do a crabby, yes, it will run. Yes, I'll put this. This one is. It is now parallelized. So if you, I don't know what Google call it. It's a delicate multi-core course. Yeah, you could use that. There's an option in the sample arguments here, which is called endpool, which you could pass on if you had multiple cores available to you. I wasn't quite sure if the cloud would allow for you.
So the CPU.
I think the GPUs are quite anyway. If you had a GPU code for example, to run. And then I wanted to briefly, because I've got my results actually very good, just to show you what's actually all stored in your posterior object that you have. So if you run the keys argument on it, you'll see all the various information that is being stored. In your posterior, obviously, it's all the parameters that we have sampled over and also the ones that we haven't sampled over, but that will just be a single data point, of course. And then you'll also see there's some reconstructed parameters. Like you'll notice here, there's a bunch of things that say chirp mass source, total mass source. Because the one thing, of course, I didn't mention, but should have mentioned is what we measure natively, of course, is detected frame masses. Masses are redshifted due to gravity streams traveling at finite speed. And so we have to assume, if you want to convert this, you have to assume, if you don't measure, Z independently, you have to assume some conversion and assume some cosmology in order to transform it into this stream. So we normally use the 115 cosmology, but I think we're going to move to 115. So and then you can also see other things. So you can see the signal to noise ratio as you evaluate your likelihood, and you draw every point as you draw a point from the trial, generate the waveform, compare it to the data, you get your SNR time series. So we also produce that distribution and store that, etc. And we often find that, as you would expect, that in the PE we get a slight increase in the matched filter SNR compared to the search, because we use a bit more, sophisticated models, I would say, than is being used in the online analysis. And then, yeah, you can plot stereo distributions, which in this case is not so lovely, but if you had done a better job, you could do that. Yeah, go ahead.
We just have these tables of
Yep.
the things, like what are different rows.
Yeah. So this is just the iterations, the number of iterations, so the number of samples that are being retained at the end, I should say, because we have this thinning process in order to make sure that the samples are uncorrelated as you step through the parameters. So in this case, we have, as I said, right, we have very loose p streams here. So we have 286 samples per dimension, which is not very much. So if you download the actual data from the LVK, which you can also do from the GWAS page, for example, you can download all posterior samples. You'll normally find there are a few thousand at least. I don't know how much how large the PyCVC samples are that you guys release on the original space.
We essentially just put out whatever NXT gives us, so it can really vary from event to event, but it's always at least order 10,000.
I don't know how useful that was, but I hope you have some idea of some of the tools. They're hopefully quite user-friendly later because you can access them for Python.
Probably everyone seeing that.
Sorry?
Well, there is some agreement. Distributions that everyone's getting.
Yeah, of course. I mean, that's the nature of the cat example, right?
It's everything random.
Yeah, they use
Same
snakes,
seed,
fine.
we hope to get agreement.
Yeah, and if we had done a better job, you know, at having set up like our run better and waited for longer, then eventually we should converge all to the same result, of course.
I'm looking at this plot, it's nicer than one.
All right, as the chair of the session, I think I'm gonna call it a mere 30 minutes late.
Yeah.
So let's thank Patricia again. Let's take a picture now.
Oh, yeah, we got on the side things.
Good day. So don't run away.
Yeah, and I should say you can just save that notebook, right? So Google Colab, when you manipulate it, then you can just save it as a copy into your own namespace, and then you can do with it whatever you want. And